Dr. Birnbaum is the former director of the National Institute of Environmental Health Sciences of the National Institute of Health and the National Toxicology Program. As a board-certified toxicologist, Birnbaum served as a federal scientist for 40 years prior to her appointment at NIEHS and NTP director. In 2009, she spent 19 years at the United States Environmental Protection Agency, where she directed the largest division focusing on environmental health research. After retirement, she was granted Scientist Emeritus status and still maintains a laboratory. Dr. Birnbaum's research focuses on the pharmacokinetic behavior of environmental chemicals, mechanisms of action of toxins, including endocrine disruption, and the linking of real-world exposures to health effects. A native of New Jersey, Dr. Birnbaum received her master's and PhD in microbiology from the University of Illinois. So we're pleased to have you join us today, and the floor is yours.
Thank you very much, Elizabeth, and thanks everyone for being here. What I want to do is give you a brief road trip through the perils of PFAS, and I've called this, remembering the movie that won the Oscar over a year ago, Everything, Everywhere, All of Us, because I hope to demonstrate to you and convince you that, in fact, these chemicals are everywhere. They are in everything, and we all have them in us. So we're going to just go ahead. Let's see to the next slide. And why is it not moving? Okay. I just did want to say that I have worked as a expert for a plaintiff for a big case related to PFAS toxicity. Obviously, that's all since I was in the government, when the only group you represent is the US government. So I wanted to briefly talk about the total number of PFAS being more than 15,000 chemicals. We're not talking about, a small class of chemicals. Sometimes people want to talk about these like dioxins, but in fact, it is a much larger class. Why do we have them? Well, they're very useful. They have been used in things like Teflon and Scotchgard, and a major source of water pollution is the aqueous film forming foams. But lots of things we really don't know what they are. They're used because they provide resistance to grease and water and oil and surfactants and so on. Now, some of the characteristics that make them so useful are also problematic. They are all environmentally persistent. Now, PFAS don't occur naturally, and there is no easy way to get rid of them. I'm going to show you some of that. They are mobile in the environment, so I should say that some of the highest concentrations that we're seeing are in the Arctic, and many of them do bioaccumulate in our bodies as well as other biota. And I think some of the things that we need to realize is that while we started off, if you look at this designation of PFAS into non-polymers and polymers, and you start with the different substances like the PFAS, which include the things like PFOA and PFOS and the sulfonamides and all that, they initially looked at long chain ones, meaning C8 carbons or longer. But in fact, what we're now finding is tremendous use of the short chains and the ultra short chains. An important thing, and I'm going to come back to this about polymers, is polymers have to be made, and then polymers undergo a life cycle with some of them break down, so that the fluoropolymers all eventually do also release some of the monomeric units as well. So, for example, we know that the per and the polyfluoroalkyl precursors like the ethers, the side chain fluoropolymers. I want to especially call out the fluorotelomers. These are a huge problem. I'll show you some data that these are extremely volatile, and all of these break down eventually to give you the perfluoroalkyl, things like our old friends PFOA and PFOS, but also some of the ethers, things like Gen-X, which you may have heard of. It's a major problem near where I live in North Carolina, and the short chains and so on. So we have this whole universe of of the fluorinated polymers. And I think what's important to realize is that sometimes for the polymers, the PFAS are side chains, which means that they easily cleave off. Sometimes they're in the backbone, which does make it harder for them to break down. But what I think we need to understand is that the total fluoropolymer market is 330,000 megatons. And what you can see is one of the biggest is the PTFE, which I'm sure you've heard of as a major polymer, as well as you've got things like polyvinyl fluoride and so on. So that there are many, many different kinds of fluorinated polymers. And the polymers represent a significant amount of the total PFAS, but at least 80% of the PFAS monomers to which we're exposed are coming from the polymers. Now, I mentioned the issue of short chain PFAS, and initially when we talked about short chain, and by initially I mean maybe a couple of years ago, we were talking about chemicals that had C4, C5, C6. They were considered short chains because they had shorter biological half-lives than things like PFOA or PFOS, or certainly things like even the longer chain ones like the C10 or the C12, for example. But now there's growing concern about what we call the ultra short chain PFAS. And there are over 1 million precursors that will eventually break down to give you trifluoroacetic acid, which is being found in high levels in groundwater wells, in river water, and even has been detected in human blood. In fact, when the Chinese study looked at it, they found that at least 97% of the Chinese blood, they could find the TFA. And I think these ultra short chains, whether they're the fluorinated refrigerants, which can break down to give you the TFA, or the C1 through C3 perfluoroalkyls compounds, will not easily be removed by our standard filtration methods that work quite well with the long chain PFAS. And then another point that I wanted to make is that new PFAS are being found all the time. Now, this happens to be a study from almost 4 years ago, where in New Jersey, they found that a plant called Solvay was making a chloroperfluoropolyether carboxylate. And in fact, they not only found it near the plant, but they actually found it as far away as they looked, which was New Hampshire. Now, nobody's looked further, but when you start looking, you start finding, and I should say these chlorinated and actually brominated PFAS are increasing in production and use. So we have some of the occurrence of PFAS in many, many different kinds of products. And I think, this is kind of a complex schematic, but it gives you the idea of how many kinds of consumer products the PFAS are found in, as well as, for example, pesticides, pharmaceuticals, and so on. And if you actually look at the largest sources of PFAS are things like, for example, production of plastic and rubber in the industrial sector, and, for example, in the commercial sector, coatings and paints and lubricants and greases. Now, I think we often think about it's in our fabric and it's in our food packaging and pots and pans. And I would suggest that if you want to buy a nonstick pot, make certain that it's labeled no PFAS, because if it's labeled no PFOA, it's going to have other PFAS in it. So how are we exposed? Well, I've already told you that these things are pretty much everywhere and in everything, and that they are solely products of industrial activity. A major source I've mentioned was the firefighting foam, which is used extensively and has led to drinking water and groundwater contamination, especially around military bases, around airports, and around firefighting stations, for example. They go into consumer goods, and I've mentioned many of the different types that we have, and they can be directly, unfortunately, and have been directly released into the environment, as well as a product of waste infrastructure. So we know that a major wastewater often contains high levels of PFAS. So whether it's coming from the environment, or from whether it's water, or whether from consumer goods, obviously it gets into food. So we know that both our animal products, including fish, are exposed. I'm going to show you some data about that. We know that drinking water is a very significant source. And then consumer goods, whether it's house dust or volatile pathways, lead to lots of human exposure. So this is just a graph that just came out in the paper about 2 weeks ago about the high levels of PFAS in surface and groundwater. And I think what you should notice, there's lots of areas where you don't see any PFAS. That doesn't mean it's not there. That just means nobody has looked so far in the surface or groundwater there. And what you can see is that pretty much, if you look at, for example, major industrial areas, whether it's in Northern Europe, Australia, China, or the US, have some of the highest levels detected to date. And this is just some recent, actually a recent graph from Environmental Working Group showing the levels in drinking water in the in the US and other sites. And again, what you see is the highest levels, for example, my state of North Carolina, where PFAS are produced by Chemours, which was spun off from DuPont in 2009. It's a major source. You see lots, for example, in Michigan. You see lots in places in Denver. Again, a lot of that is near the Air Force Academy and the Air Force Base, lots in, up and down the coast. Again, many of the areas you don't see PFAS are because nobody has looked very much. That will change with some of the new regulations. And then I think this is a really a fascinating study that just came out about a year ago. EPA collects fish samples from over 500 sites around the US, and these are freshwater fish. They make compost from 10 different fish in a certain area, and then they measure lots of chemicals in them. Well, when you look at PFAS, what you found that out of over 500 composted fish samples from around the country that were taken, essentially all of them had elevated levels of PFAS. And in fact, PFOS, the C8 sulfonic acid, PFAS, represented 75% of the PFAS in these samples. But again, what you can see is lots of samples around the Great Lakes, lots of samples kind of going down the Mississippi. What you see them pretty much is around the country. So there is some data that, for example, some of our Southeast Asian populations living and eating fish from a lot of fish from the Great Lakes have elevated levels of PFAS in their bodies. Now, so that suggests that, or demonstrates actually, that if you eat a lot of fish, you may have higher levels of PFAS. And these are just some data from a few years ago. One from the Faroe Islands, where the children who eat a lot of whale meat, which has high levels of PFAS because they are top predators in the food web. What you see is those children have higher levels. And then some data from Massachusetts showing that people who ate more shellfish had higher levels of PFDA, which is the C10 relatives of the C8, the well-known C8 PFOA. So again, if you eat a lot of food, especially fish or seafood, you're likely to have higher PFAS levels. And then this is some data looking at PFAS, for example, in our food supply. We know that there are many different kinds of PFAS in our food supply. And unfortunately, what we found is that, for example, in a lot of food packaging is a major source, but I should say certain kinds of plants that are grown in contaminated soil or contaminated water is used to water them will also have elevated levels. We've moved away from the PFCAs, the things like the long chain PFOA and PFAS, to the shorter chain, but the fluorotelomere alcohols, the FTOHs, have been substituted, and I think I show it later in the slide, but FDA has recently banned their use in all food packaging because they all break down to give you the PFCAs. So this is just some data from inhalation exposure. And this was indoor inhalation exposure looking, for example, in California, Rhode Island and outdoor clothing. And what you find is very high levels of the fluorotelomere alcohol in the air, in outdoor clothing stores, for example, or in kindergartens. And I think, again, as I've just mentioned to you, the fluorotelomere alcohols all break down eventually to give you the perfluoroalkyl acids. And what you see is there's lots, especially of the C6 and the C8 fluorotelomere alcohols. And so I've kind of talked a little about ingestion from water and food, and then inhalation exposure, but there's also some dermal exposure. So a big concern now among the firefighters is that their gear, I mean, not only do they used PFAS containing air film forming foam to help put out fires, but their gear is loaded with PFAS. And in fact, it's required by the Firefighting Association. And there's a lot of concern that this can get into their skin, because you have PFAS both in the outer shell and in the moisture barrier, and you sweat, and this gets it on the skin. I think we have to remember, however, that, the PFAS here are really serving a health protective function. We don't want our firemen going up in smoke, and we don't want them to die of heat prostration. But there is a great deal of effort developing new gear which doesn't contain as much PFAS as least. So I told you how we all get exposed, because it's everywhere and we all have it in our bodies. And this is true around the world, wherever people have looked. I will say there's even some data, for example, from Alaska, from our Inupiaq peoples up there being heavily exposed. But at least 98% of people in the US have measurable amounts of PFAS. And the levels of PFOA and PFOS, and I haven't yet told you, but in fact, the 3M was the sole producer of PFOS, and they stopped making it in 2002. PFOA was produced by at least 6 different companies, but with an agreement with EPA, they all stopped making PFOA by about 2013. So certainly PFOS levels have come down in the environment, in people in the US. PFOA hasn't come down as much, and it may actually be kind of becoming flat. But some of the other long chains like PFHXS and PFDA, there really hasn't been much change in them. This is just some indication of the levels of exposure from workers as compared to the general public. And I think the importance here is that Italy has had a real problem in the Veneto region with a lot of exposure to, and this is predominantly PFOA and PFOS. So you can see there that their concentration in the biological matrix is almost in the ppm level, which is kind of amazing. We find with the general population in the US, non-occupational is usually below around the neighborhood of 1. And I'm going to come back to this as well. But if you look at, for example, some data from Spain or the US in 2010, levels were higher, up around 10 parts per billion. And if you look, for example, at people, for example, in Australia, 20 years ago, levels again were around 10 ppb. So, and again, I think what's interesting is in China, there's data saying if you just happen to live near a chemical plant, your levels may be as high as 100 parts per billion. So these are real concerns for the general population, as well as people who are occupationally exposed. And while I've shown you that the PFOS and PFOA levels are coming down, especially PFOS in the US, basically since the phase out of those 2 major PFAS. If you look at the short chains, ranging from the PFBA to the PFBS to up to the C6 and the C7, what you find, and this is data from breast milk, and I should mention that in fact, we basically pre-expose all our infants, both in utero and lactationally, to PFAS. But you can see that the levels are going up. Now, again, if it's in your drinking water, you can get some kind of estimate of what the level may be in you. So this is some lovely data from Gloria Post, actually, from the state of New Jersey Department of Environmental Quality, where, for example, if you look at the levels in the mean US population, what you can see is that it's less than 2 parts per billion. But at the 95% level, it's up at about 5 parts per billion. But then if you look at the people who actually have more water ingestion, for example, and if their drinking water concentration goes up, what you can see here is, for example, that as the as the concentration in drinking water goes up, your levels in your blood go up significantly as well. So I'm going to go through this very quickly. This is kind of the history of PFAS exposure, but realize it was first invented at DuPont by a chemist in the 1930s, and PFAS production really took off in the late 40s and the 50s. But, you know, we also began to get data that we began to see. For example, in 1962, a DuPont scientist raised concerns regarding health risks of PFAS in internal documents. Of course, those were not shared, actually, until litigation made them become available. But by the 1975, 3M knew that PFAS were being found in blood of the general population. They were finding it in the serum of workers. There was data on cancer in animals and so on. And there were also concerns about defects in children born to women who were on the line producing PFOA in Petersburg, West Virginia, which was the major site of PFAS production. By 2000, we essentially knew that all Americans were exposed, and 3M actually in 2000 announced they were going to phase out PFOA, not only PFOA, but PFOS by 2002. And DuPont began to produce PFOA in Fayetteville, North Carolina, and that Chemours was spun off from them. But in 2001, DuPont was sued in a class action lawsuit. And if you haven't seen Dark Waters with Mark Ruffalo playing the attorney Rob Billitt, I highly recommend it to you. And we began all kinds of human data, as well as lots of animal data began to come out. So I think some of the most important was the fact that we were seeing immune system effects in children to PFAS, as well as other data. And we began to find novel PFAS. People began to look more broadly than PFOA and PFOS. So what about the health effects? And I happen to love this diagram that I took from ATSDR's assessment of PFAS toxicity in 2018. And that's basically, don't think I've met a organ system that PFAS haven't liked to impact. So we know that PFAS are endocrine disruptors, for example, not only on the thyroid, but affecting estrogen, androgens, and many other hormone systems. We know that PFAS are not only nephrotoxicants, but are also associated with increase of kidney cancer, as well as testicular cancer. And there's growing data. I just saw a paper this morning, showed an increase in ovarian, prostate, and breast cancer as well. PFAS suppress the immune system, but in addition to suppressing it, they also cause an increase in autoimmunity. PFAS are liver toxicants, and there is some suggestion they may also be liver carcinogens as well. People who have higher PFAS have higher levels of low LDL cholesterol as well. There are impacts on the pancreas and the associations with increased risk of type 2 diabetes, as well as increased obesity problems. And there's growing evidence for impacts on neurodevelopment. So how do PFAS do this? Well, this is not a simple answer. We know that the peroxisome proliferator active receptors, the PPARs, and there are at least 3, if not 4 types of PPARs are activated, and this plays a role in fatty acid metabolism, but also that's PPAR alpha especially, and PPAR gamma is key related to diabetes and obesity. But we know in addition, there are also lots of alternate receptors, including the androgen and the estrogen, CAR, PXR, FXR, and so on. PFAS can also inhibit fatty acid transport and can directly interfere with mitochondrial function. PFAS are all amphipathic, so that they can bind both to the lipid and the aqueous regions of cells. And this was a nice paper, it came out about a year and a half ago, where they were looking at the binding of a whole 49 different PFAS to different kinds of steroid nuclear receptors. And what you can see is, for example, something like mineralocorticoid receptor has high binding probabilities, as does ER beta as an antagonist and an agonist. And for example, the androgen antagonism and agonism as well. And the PPARs, which are the one that so much work has focused on, the probability of binding is not as high, but we know it happens. So this is just an example of how bioactive this class of chemicals is. So what are some of the key research questions that we need to be dealing with? Well, some is, what about the total organic fluorine analysis? Are we measuring 90% or 10% of PFAS present in the sample? How do we get rid of PFAS? Filtration, incineration, landfill, and I'm going to come back to all of this. We need to begin to ask the question that was asked in the development and the restriction on the chlorohydrofluorocarbons related to the ozone hole. Is it essential? Where do we really need chemicals, and where can we replace with safer alternatives? And we've got to be sure that if we go to alternatives, that our substitutes are safer than the originals. In the history of PFAS, that's not the case. We've moved from the C8 compounds to, for example, the C6s and the C4s, and they do, and the ethers, and they do the same things. And can we begin to look at PFAS as a class? 15,000 chemicals. There's certainly too many to ever do proper toxicity testing. And the question about doing a class approach was taken to the National Academy by the Consumer Product Safety Commission related to flame retardants in 2019, and the National Academy's opined that an approach that uses subclasses to assess the chemicals is certainly justifiable. So what about all these other PFAS? And this is a slide that I have from a couple years ago. And I think this talks about 4,700 PFAS. That's all we really knew about 5 years ago. Now we know there are over 15,000. And if you looked at extractable organic fluorine, that doesn't include the polymers, and they're only detecting about 200 of them. This is some data with what was found in drinking water in Massachusetts. And what you can see is that the unknown is by far the vast amount of what's there. And as I said, this doesn't account for the polymeric information. Some recent studies looked at what's actually measured in drinking water. And if you look at what EPA currently, or up until this past year, was measuring, well, not too much of it. Then they developed another method which does detect more. It looks at some of the, for example, the fluorotelomere compounds and some of the shorter chains. And then in this study, they found a whole bunch of others that weren't found by the EPA methods. But then you've got loads of other unmonitored PFAS that are not being looked at. And some of these are, for example, are the pharmaceuticals that are present in municipal wastewater treatment plants. So what you can see is that some very, very well-known drugs, and I'm looking, I know, for example, Prozac and fluoxetine and a number of others are all present in drinking water. But this is, again, looking at non-polymeric forms, not the total organic fluorine that might be in the water. So if you measure 16 PFAS, which is often what's done, you really only measure about 2% of the total. And when you try to look at the extractable organic fluorine, most is unidentified. So what about, for example, how do we do these chemical analysis? And I wanted to point this out even more clearly. If you look at the targeted PFAS, what you find is that the most really analytes that people have standard for is about 80. And will get you about 80. If you do a non-target analysis and you do different kinds of high-res mass spec and GC and liquid, all different kinds of analyses, what you find is you pick up lots more PFAS. But then you can also look at the total organic the total fluorine. And this is a method that's being used extensively where you measure all the fluorine in a sample and you subtract the inorganic fluoride. For example, that might be added to your drinking water. And that gives you another measure. And then there are now methods being developed to measure total organic fluorine, which would be the closest proxy for the total PFAS. One of the points we need to mention with the targeted PFAS, we have sensitivity down around 1 to 5 parts per billion. When you get up and you're measuring total organic fluorine, you're in the neighborhood of a parts per million. So we need a lot more work done to improve sensitivity here. Okay, well, I've told you these chemicals are everywhere. How can we get rid of them? And I think it's kind of depressing. Currently, there is no safe way to dispose of PFAS at scale. We can filter out most of the targeted PFAS from drinking water. I've already told you we don't filter out the ultra short chain, the C1, 2, and 3. You'll filter out some of the C4 to C6s, some of the ethers, but not all of them. And then what do you do with the contaminated filters? Well, I can tell you, and you may have to put them into a lined landfill, given what was announced this week by EPA. There's lots of people working to find safe and destructive technologies that would actually destroy PFAS, actually demineralize PFAS. But from my point of view, the only thing we've got to do is really stop making all these compounds. And we also need the polluter to shoulder the costs. So some of the challenges of PFAS destruction, and EPA has just released some interim guidance that present the latest best available science, is that the chemistry is so complicated. The carbon-fluorine bond is the strongest bond in organic chemistry. What often happens when people think they're getting rid of PFAS is they just create short chain, ultra short chain PFAS. They don't actually get rid of all the carbon-fluorine bonds. They break the carbon bonds, but not the carbon fluorine bonds. And we really don't have field data for this. So what is EPA currently doing? And since 2021, they have strategic roadmap goals so that all parts of EPA are invested in trying to deal with the PFAS problem. And their goals involve both research, restriction, and remediation. But I've already told you it's hard to remediate. And we have lots of research data, so we really need to talk about restriction. This is just a slide I put together from a recent EPA draft, focusing on the toxicity, a risk assessment of PFNA, which is the C9. But what you can see is compared to many finalized EPA documents. Again, these are on PFHXA, which is a C6, BA is C4, BS is C4, GenX, which is one of those ethers, PFOA and PFOS. And what you can see is that when you look, you find the same thing by essentially all the chemicals. The yellow or the gray is where it hasn't been looked at. The yellow is where we really don't have adequate data often to assess it. But if you look at effects on endocrine disruption, effects on the liver, effects developmentally, for example, what you see it. And then if you look at cancer, we have no long-term bioassays in animals that have been done for anything, or at least that we know of, for anything other than PFOA, PFOS, and GenX. And in all cases, these there were positive responses. So let's talk about the risk assessment of PFAS. And one thing I want you to note is with a little graph here in the corner, I think what's important here is if you look at the timeline, what you see is as we learn more, the risk assessment, for example, the guidance for drinking water or the maximum contaminant levels keeps going down. So if you go back, to 20 years ago, you see it was up in the area of 100 parts per billion. Now we're in the parts per trillion range. So the European Food Safety Authority, which sets tolerable weekly intakes, 4 years ago, looked at 4 different PFAS where they had data and set a total exposure of 4.4 nanograms per kilogram per day and concluded that much of the European population, their ingestion exceeded that. And they based their analysis on decreased vaccination response. That's the immune suppression. ATSGR in 2021 released minimum risk levels. These are not regulatory, and they picked the same for PFAS that they said they had enough data to base regulations on or base policy on. EPA, and we're going to come back to EPA, had non-regulatory guidance in 2016. They set a lifetime health advisory of 70 parts per trillion. But in 2022, Raditha Fox, who was the assistant administrator for the Office of Water at EPA, said that the interim health advisories for PFOA was 0.004 and the PFAS was 0.02 parts per trillion. The states have not been waiting for EPA. They've moved ahead. So, for example, Maine and Massachusetts set a maximum contaminant level for the sum of 4 PFAS of 20 parts per trillion. Vermont took out one of the PFAS and set it at the same level. And again, critical effects, developmental, hepatic, and immune. Now, I already mentioned that EPA in June of 2022 set interim advisory levels extremely lower based on all the new science that came out. And EPA, when they announced these, kind of knew that there was no way that that would be the actual level that would be set when they announced drinking water regulation, but they wanted to give the water utilities a heads up of what was coming. And I should mention that last November, the International Agency Research for Cancer did a classification for PFOA and PFOS, and they concluded that PFOA is a group 1 human carcinogen, and that PFOS is a group 2B, which is a probable human carcinogen. And a lot of this was based on the limited data in humans and sufficient data in animals plus mechanistic data. So I think this is a very important international finding. And EPA, just last February, proposed to list 9 PFAS as hazardous constituents under RCRA, which is your hazardous waste law. And this expands EPA's ability to address these PFAS. And the governor of New Mexico had actually petitioned EPA to do this in 2021. And I think what's most exciting is exactly 6 days ago, am I counting right? Yes. PFOA and PFAS were designated as hazardous compounds under Superfund. CERCLA is the law. And now the polluter will have to pay to clean it up. This is huge. And just 2 weeks ago, EPA actually promulgated regulatory standards for 6 PFAS. For PFOA and PFOS, they concluded that they were likely human carcinogens, which means that their maximum contaminant level goal is 0, that there is no safe level for these chemicals. But then the regulatory limit is what's called an MCL, maximum contaminant label. And this includes not only the health effects, but technological, economic, and sociological considerations. And these were set as 4 parts per trillion. And that number was largely picked because most water utilities can successfully measure that level of contamination. 3 other PFAS, the C6 sulfonic acid, PFHXS, the C9 carboxylic acid, PFNA, and GenX. They actually set the MCLG, was based on non-cancer effects, and they set that equal to the regulatory limit of 10 parts per trillion. But then they did one more thing, which is, I think, pretty exciting. They said, we're going to tackle the idea that these chemicals often occur as a mixture. And so they used a hazard index approach, which has been used repeatedly by Superfund. It's not totally new to the agency. And if the hazard index for a mixture of 2 or more of these chemicals exceeds 1, then that would mean regulation has to occur. Now, it isn't like all the, I think it's 26,000 or more municipal water authorities in the US have to meet these standards immediately. They have 3 years to actually do their monitoring, and it won't be until 2029 that they have to implement solutions. So that our municipal water authorities have time. I think it's important to realize none of this pertains to well water. So if you're on a private well, you may want to get your water measured, but there is no regulatory authority to regulate private wells. Now, there are several other federal regulations on PFAS. Just about 2 months ago, FDA announced that they were removing all PFAS from food packaging, and that was largely the fluorotelomere alcohols. At this point, they had actually removed the long chain PFAS about 6 or 7 years ago. The Department of Defense can no longer have PFAS in their airform filming foam. By the end of this year, they could no longer use it even in practice and training by 2020. And then the Federal Aviation Authority does no longer require PFAS to be used in AFFF in domestic airports since 2021. So as I mentioned before, the states are moving ahead, and more than half of the states have considered restricting PFAS last year. And this year, we believe the data coming from Safer States indicates that at least 36 states have at least 450 bills on toxic chemical related policies with PFAS, plastics, and cosmetics as key focus areas. And I should stress with you that many cosmetics have PFAS, many plastics have PFAS as well. When I take a look at these maps, though, it is a little concerning about all the areas where states are not moving ahead. Again, with these binding restrictions in levels in drinking water, that will require all the states to get moving, at least on that source to human exposure. So 30 states actually had already set drinking water, groundwater, or surface water guidelines. 8 states actually had regulatory limits. 2 states have guidelines which are more restrictive than EPA's MCLs, Illinois and Vermont. So go Illinois of 2 parts per trillion. If these are already in place, they can stay in place. It isn't like now Illinois has to default to the 4 parts per trillion. And 23 states are looking at more than just PFOA and PFOS. 36 states are in the process of banning or restricting PFAS containing the air film forming foam. Again, if it's got PFOA or PFOS or those other 6, it's going to be, they're not going to be able to use it. And it's being banned in major food contact materials. I should say that Denmark went ahead and banned it in all food contact materials 4 years ago, and it's being banned in textiles and furnishings. So I'd like to switch to Illinois briefly as we approach the end of my presentation. That in fact we have PFAS. These are your groundwater sources for PFAS. And what you can see is that, for example, in Western Illinois, and I don't know Illinois geography well enough, that may be, I don't know if that's Rockford or what, but it's interesting that PFOA, the CO8, is a major determinant. If you look, for example, along the Great Lakes, you see a different distribution, including more PFOS. And then, for example, in the middle of the state, what you see is an awful lot of the PFHXS, as well as, for example, and down towards Southern Illinois, PFHXA, and so on. So this gives you an idea where 4 years ago, 3 or 4 years ago, PFAS that were, and only what people were looking for, this is what was found in your state. And Illinois has gone out with statewide health advisories. So PFOA has a guidance level of 2 parts per trillion in water. And that has now, I believe, been finalized. PFHXS is 140. Well, guess what? The new EPA regs for PFHXS is an MCL of 10. So that is way higher. PFOS is also 4 from EPA. So that'll have to be regulated. PFNA is also 10, so that'll have to be regulated. So I think this is giving you some idea of how states are going to have to respond. And this is just the 3M's Cordova plan on the Mississippi River upstream from the Quad Cities. And that was the area that I showed you had lots of PFOA, for example, in the groundwater in that area. And this is some work coming from Michael Hawthorne, who is an excellent environmental reporter. I've worked with him many times in the past, just from a month ago. So what do we do about it? So the National Academy of Sciences convened a consensus panel in 2002 and concluded that at that point in time, they believed that there was sufficient evidence of the immune suppression, which is the decreased antibody response, to the dyslipidemia. I mentioned the elevated LDL cholesterol, decreases in infant and fetal growth, and increased risk of kidney cancer in adults. And there was also limited evidence of an increased risk of breast cancer, of liver enzyme alterations, increased risk of pregnancy-induced hypertension, including preeclampsia, increased risk of testicular cancer, thyroid disease and dysfunction, and ulcerative colitis, which was an autoimmune condition. And I should say there is so much research coming out on health effects of PFAS that if they were to look at the data today, I think they would add additional adverse, they would say sufficient evidence for many other health effects. So the National Academies actually recommended some opportunities for clinical follow-up and care for PFAS exposure. And they said if your levels are below 2 parts per billion, they don't think you're going to have adverse health effects. I could say the more we learn, the lower that number may go. But if your level was between 2 and 20, they say there could be a potential for adverse effects, and they encourage reduction of PFAS exposure and prioritize screening for cholesterol and hypertensive disorders and breast cancer. And if you're above 20 parts per billion, they think you really need to be screened for dyslipidemia, you need thyroid function testing, and you got to keep looking for kidney testicular cancer and ulcerative colitis. Now, I should say that just a month ago, CDC actually came out with some specific guidance, based upon this National Academy reports. CDC came out with guidance to clinicians. And when CDC said this should be done, hopefully that will mean insurance will start paying for these blood tests because they are not inexpensive. So how are we going to go about managing these chemicals? I think I should say that the European Commission is way ahead of us. In 2020, they released a whole strategy for sustainability towards toxic-free future, and they called out PFAS in that. And they basically said PFAS has to be addressed as a group. They're a global concern. We've got to have better ways to get rid of what we've got, and we've got to look for safe substitutes to PFAS. And in just last year, the European Union has proposed a ban on all non-essential, non-intentional uses of PFAS. I published a paper along with others in 2020 where we called for a class approach to regulating PFAS because they're all persistent, accumulative, mobile, and hazardous, and there are too many of them to ever be adequately tested. Plus, the limited amount of information on a limited number of PFAS is we see adverse effects from all of them. So I mentioned the issue of essentiality before, and this is part of the universal PFAS restriction proposal from the EU that was just a year ago. And again, targeting a whole class of PFAS and covers all uses of PFAS, including manufacturing, and it's currently under consultation. But in most cases, there are alternatives generally available. For example, you don't need fluorinated hydrocarbons for example, refrigerant gases. You don't need it on textiles or food contract materials and so on. We do need some new approaches and innovations. For example, some medical devices and pharmaceuticals and laboratory uses. There are used in a lot of semiconductor manufacturing, but there are some new alternatives being developed. And then we really don't know about some medical devices, the energy sector, pesticides, and pharmaceuticals. There are at least 90 pesticides which are PFAS. So given this situation, are we approaching what I've called PFAS, the mother of all toxic torts? Are they the next big industry scandal? As I've mentioned, 3M voluntarily stopped making them after they finally notified EPA in 1998 that they'd known since 1975 that these were in the general population. DuPont also voluntarily agreed to stop making and using PFOA. But while they're widely produced and allowed in the marketplace, they've been underregulated and insufficiently vetted for safety for more than 50 years. They do have attractive properties, but there are no widely usable remediation approaches. So I just mentioned some recent court judgments against the polluter, and they're just a drop in the bucket compared to their annual sales. So this was actually data from 2018 net sales data. And what you can see in Chemours, less than 10%, or about 10% of their annual sales they had to spend for judgment. And that was really related to Chemours literally dumping Gen X and other PFAS into the Cape Fear River in North Carolina, leading to contamination of the entire river basin and very high levels in drinking water in Wilmington, North Carolina, a city of over 300,000 people. And 3M had a judgment of 850 million to compare to 32 billion. Now, I should have done the calculation, but what's that, 2.5% or something of their net sales. Now, things are changing a little bit. Last summer, there was a $1.2 billion settlement against DuPont, Chemours, and Corteva to clean up drinking water from AFFF contamination, and a larger one against 3M of $12.5 billion. And I think what it's important to realize is that 3M announced in November of 2022 that they would no longer make any PFAS, nor would they use any PFAS after 2025. So thank you all. Just some pictures of where PFAS is, and I'm happy to answer any questions. Thanks a lot.
Wow, that's a lot to digest and a little bit scary, but very exciting that there's been movement on policies and movement from companies taking PFAS out. We have time for questions. So, Emily, do you want to do the one in Zoom?
Yep. The first question says, regarding the relationship between the consumption of some types of seafood consumption and PFAS concentrations, what is driving this? Are consumption advisories considering the relative health benefits of seafood consumption to the risks of PFAS exposure?
Okay, that's a great question. People are starting to look at that, but I can tell you that I haven't seen anything published in that. But if you look at other persistent pollutants like the dioxins and the PCBs and some of the brominated flame retardants, when you look at that, you find out that that given the levels in seafood contamination, they don't totally overweigh the risks. And for example, women who have higher levels are giving that to their unborn babies as well as their young children as well. So there certainly are benefits, but then not all seafood is as contaminated as others. So if you look at, for example, lobster, at least off the east coast of the US, are much more highly contaminated, for example, than shrimp. So, as we have more information become available, you may be able to choose your type of fish or seafood. I personally have a lot of concerns about, especially some of our indigenous populations and our populations who eat lots of freshwater fish, and the levels of exposure that they are getting from their diet as well. And certainly we don't want to tell people not to eat healthy protein.
Great. And we have a couple more questions here on Zoom. The next one says, does technology exist to detect the unidentified PFAS and it is just not common practice, or are these unable to be identified due to technological limitations?
Well, it depends what question you're asking. Remember, for many years, people were just looking for PFOA and PFOS, and then they added the C9 and the C10, and sometimes the C11 or the C12. And then they started adding the C7 and the C6. And then they started adding like the C4s and the C5s. And some of it was driven by what kind of standards were available. So we don't have standards for 15,000 PFAS. We really don't know what many of them are if you do untargeted analysis. And you can often identify up to a couple hundred PFAS in your samples. But I personally think the total organic fluorine is the way for us to go forward and try to get a measure, use that as at least an indication of where we may have problems from PFAS.
Great. And the next question says, is there much known about what industries are switching to so they won't use PFAS, but what they are switching to, has that been evaluated, or are there concerns about that?
It's a wonderful question. And as I indicated, unfortunately, certainly we have a history of regrettable substitution where we move from a chemical that we know is bad to one that we just don't know anything about. And then that turns out to be bad too. So I don't have a good answer for you. I think more testing, if you were in the European Union, you do have to test chemicals before they go on the market. Unfortunately, in this country, under toxics and the Lautenberg Safety Act, the revisions of TSCA from 2016, pre-market testing is really not required extensively. We assume chemicals are innocent until proven guilty. And what I'm trying to encourage people to think about, if you can move to a new production process without major changes, you just change the chemical that you're using, why would we think the biology would change? Anyhow, so I think there are some areas where I think there are ways sometimes that you can do substitution for for the solution. In other words, focus on the solution instead of the process and say, what are you trying to achieve? And is there a different way to achieve this?
Great. And the next question is, the chart you showed linking drinking water concentrations to blood is insightful. I was wondering how food sources compare to drinking water as a source of PFAS.
That's a great question. And what EPA says based on their source apportionments is that unless your water is quite contaminated, and by that, they don't really define that, but I think it means instead of in the range of, for example, 10 parts per billion total, although now parts per trillion total, although now we're saying you have to regulate if you're in that neighborhood. Your drinking water may only account for 20% of your exposure, and food is the other major source. I think we have to begin. I'd like to see another source apportionment done, because many of these were done focusing only on the oral route of exposure. I don't think in most cases dermal is a very major route, although there's a little dermal exposure that does occur to all of us. But I think inhalation is a much more important route than we often give it credit for. We know that dust is highly contaminated, house dust or office dust with PFAS. And of course, anything, if it's particulate, you'll often swallow it, not just inhale it. And so then it becomes an ingestion exposure as well. But I think inhalation of, for example, of these fluorotelomere alcohols, we really don't have the data to say when you take a shower, what is your exposure level? You're not going to get a lot of exposure to, say, PFOA or PFOS or even, PFHXS or something. But what about the fluorotelomere alcohols, which are volatilized? And then you'll take them into your body and they will break down metabolically to give you, for example, PFOA or PFHXA or something. So I think in general, food is probably our major source of exposure. And we know, for example, that people who eat a lot of fast food tend to have higher levels than people who don't eat a lot of fast food. And that's probably because of the packaging.
Lee, do we have any on Huba?
No, there's none on Huba right now.
Okay. Emily, do you want to ask these last two and then we'll need to stop? Okay.
Sounds great. So the next one says, how long in your estimate will it take for the toxicological science to fill in the gaps on the impacts of individual PFAS?
Years, many, many, many years. You know, I started studying PFDA in the late 1980s, and I was studying that because it was used in some of the air film forming foam by the Department of Defense. And I can remember I had some colleagues who started studying PFOA a little bit at that point of the late 80s, but they were mainly looking at liver effects and thyroid effects. The huge push in studying PFAS began when 3M announced that they were getting out of the business in around 2002 at that. So if you actually look at a plot of amount of papers, you know, they just went up exponentially. But we're looking at over 20 years of major research before anything gets done as far as regulation. Now, I think, so as I've said a couple times, we're never going to have all the information on 15,000. There are some new approach methodologies which are being used, a lot of in vitro tests, some in silico modeling kind of approaches to look at another 150 or so PFAS. And some of that data has been published from US EPA work as well as some other work. And as I said before, most of the chemicals can do many of the same things that the traditional PFAS has done. So if we wait around for individual testing of lots of other PFAS, we're waiting clearly 10, 20, 30, 40 years for even that. So for example, I showed in that one little chart, kind of a heat map of PFNA, which EPA just released a draft risk assessment on that, but they don't have the cancer data on these things. And I think today they're probably not going to get that information on the compounds. So the kinds of data that's being generated are either the in vitro kind of, in vitro and in silico kind of approaches, or some short-term kinds of approaches. And they're only going to have it on the chemicals that they can get enough of to actually test. And I should mention that while there are over 15,000 PFAS that have been detected according to EPA's Office of Research and Development, and you can go on an ORD dashboard and see them all listed, not all of those are intentional products. Some of them are, you know, byproducts from production of intentional products. Some of them are breakdown products, either atmospherically or biologically. So I think that it's going to be a long time. Now, that being said, I see no reason why, especially under TSCA Section 4, that industry couldn't be required to fund unconflicted testing of a large number of the chemicals they're actually producing. But you're looking at, you know, to do a cancer bioassay, you're talking probably 3 to 5 years before you'd have any results to look at.
Great. And then we have our last question here. As I know, many legacy PFAS are going to phase out, but more emerging PFAS are being produced and used. For example, clean energy associated PFAS will be widely used with electric vehicle development. How do you think about these emerging ultra short chain PFAS? How about their toxicity or regulation?
So it's a great question. And the answer is I don't have a good answer, but I think we know that the ultra short chains are less acutely toxic, but at high doses, they are highly toxic, that they, in fact, we're finding very high levels in some water supplies when you look at it. And my understanding is if you look in house dust, there's some study coming out of the University of Indiana, that almost 90% of what's in house dust are these ultra short chain PFAS. So I think we need to be encouraging and pushing industry to develop safe alternatives, new processes to achieve the goals of energy independence and that don't cause more PFAS problems and more climate change. Thank you.